is happening, chemical kinetics is there, and also the heat transfer, everything will come into the picture. So it is a multi-physics problem. So in order to solve an unsteady multi-physics problem, you need a very high computational power. Even in order to do that, your laptops or any small desktops cannot handle it properly. If you really want to do a proper study, I'm talking about. So in that case also, we need a high performance computing. Next, let's see who are really using high power computing nowadays, actually. So, for instance, aerospace. We all know like aerospace engineers using that. For example, like if I want to simulate now, currently we are working on an airplane. Let's say it is like we are using 12 crore to 15 crore number of cells. If I'm using a single processor, it takes at least let's say like 1 month to run one case. So, but what to do? We are using parallel computers actually, which means 120 processor or 80 processor together run the same problem. So the problem is split into 80 pieces. So we could run that within 2 or 3 days time. Likewise, and manufacturing area also people are using a lot of parallel computation for autonomous and all those things. And also finance technology. This is one of the important technology where people are using high performance computing. So what I really want to say from here is like if you see genomics and your sequencing studies, DNA studies, and biomechanics, everywhere people use high performance computing, and oil and gas everywhere. So here, what I like to give you as a take-home message is, although I'm going to talk about high performance computing towards aerospace engineering, or especially in the computational fluid dynamics, how it works and how to develop, but this same application, same methods can be applicable in any kind of field, not necessarily only computational fluid dynamics, or not necessarily only in aerospace, and also in any kind of field. For example, as I mentioned here, finance, technology, everywhere. So this is a data who is really using high performance computing in this world. So you can see that. See, these are all the data how much people are using actually. See, finance team is using a lot actually, and not specified is too much, which means like they are using for any other purpose. We don't know exactly. They don't want to specify a single application, which means maybe they are using for different applications, not a single application. Likewise, and CFD is a small part. Aerospace is a small part, but as you see, finance and geophysics people using a lot, and weather and climate research people are using a lot of this high performance computing. Now, what is the benefit? Let's talk about what benefits are having if I'm using a high performance computing. First, speed. I can finish my calculations as soon as possible. And then cost. I can reduce the computational cost actually, because I'm reducing the time. Eventually, if I'm reducing the time, money is actually connected with the time. So always my cost will be reduced. And fault tolerance. So this is one of the important thing. As I said earlier, like it is a cluster, which means so many computers are connected together. So for instance, one computer is not working. Then I can shut down that and I can use other clusters to operate the simulations or operate the any work calculations I'm doing. So I'm not rely on a single computer now. It's a cluster. So many computers are together there. So it is an important thing. For example, you can see, let's say YouTube. How many times you've seen that YouTube was shut down? Okay, they never. Have you ever heard that? Okay, they say that okay, our server is gone, or else I can say like, oh, our computer is not working, so we are not working. But you cannot hear that. But you can hear this. Actually, my computer is not working with your friends or anywhere very closely with you. The reason is very simple. They are using YouTube, Facebook, everywhere they are using cluster computers actually. I mean high performance computing, and all the computers are put it together. So if one computer is going down, it's not a problem. Another one will take care. So in that way, it will work. Now let's back to the business. HPC in aerospace, where we are really using. Here I'm shown only very few examples actually. Aeroacoustics, for example, this is a UAM, I mean urban air mobility vehicle. Actually, people are studying, and see here with all these six propellers and with these simulations, maybe they will be using at least 20 to 30 crore cells actually. So and moreover acoustic study. So definitely a fine mesh is required in order to study this. So in that case, definitely a high performance computing is there. Without that, not possible. Then full engine simulation with large eddy simulation. Large eddy itself quite expensive method, but they are simulating large eddy for a full engine. It's literally complicated. It's impossible without a high performance computing. But you may think, okay, why not? We can split them into pieces and we can do small studies. That is true. But if you think very carefully, a full scale study is much important and much necessary for understanding the physics. Then 6DOF of here this airplane is dropping its fuel tank, actually excess fuel tank. So this kind of study 6DOF, the time steps are very small and we need to run thousands of time steps. It's very not easy to simulate a 3D 6DOF without HPC. And flutter analysis, a whole airplane flutter, you can see it is a coupled phenomena, like it will be connected, structure solver is connected with the airflow solver. So it is what I can say, like a closed loop simulation. It takes huge amount of memory. Then as I mentioned previously also, the reaction flows and combustions. Now, some terminologies. You may hear like some people say, okay, HPC I'm talking about now. Then some people say that parallel computing, likewise. Okay. So, what is the difference actually? That you should know. It's important. So, HPC, any computing facility. HPC means what? Any computing facility which can do the calculation faster. We can call them as high performance computing. It can be anything. For example, you can work on the hardware, you can work on the software. However, you have to make the computation faster. That is your HPC. But parallel computation is actually, we will increase the parallelization of the process. I mean, how the process is going. It is purely upon the programming actually. So here also some difference are there. For example, um, we can use vectors or else parallel CPU or GPU, I mean graphic power unit or CPU. Likewise, you can use anything. Overall, actually, the high performance compute can cover the parallel computation. Parallel computation is a part of high performance computing. Okay, so this is the difference between your parallel computing and high performance computing actually. Now, this is like some interesting quotes. People talked about parallel programming. So you can read about like some quotes told by very famous people in the field of computation. For example, even Steve Jobs told one time, the processing industry is adding. You can see it's like many cores and many number of processors is added. You can see now mobiles also coming with 4 processor, 6 processor. So likewise, he told irrespective to that only, actually mobiles and laptops, more cores. Nobody knows how to program those things. I mean, 2, yeah, 4, not really. 8, forget about it. Which means it's complicated. I mean, people are still, I cannot say fully agree with this, but still it is true. When it is 2 processor, you can efficiently use both of the processors. 4, not really okay, but once it is number of processor increasing, end of the day, the story here is once the number of processors increasing, utilizing the processing power efficiently is not easy. It need a hardcore programming and very good logics behind that, or else it's hard to do the programming. That is the take-home message. So now, Steve Jobs. I hope everyone of you knows Steve Jobs. Steve Jobs told about it. Then what is the reason? Let's talk about that. See, 3 reasons. One thing is memory wall challenge actually. So every processor is actually limited with the memory. Actually, for example, your laptops, I can say like okay, 8 GB of RAM or else 16 GB of RAM, but everything is limited. You although you are increasing the processor, every single processor has some kind of limitation in the memory actually. Power. You are increasing the number of processors. How much power is required is really going to be very high. That also, but we are running only one laptop and one computer is not a problem. I'm talking about 10,000 cores or 1 lakh cores, 1 lakh processors. How much power it will take at a time? It is not easy to manage actually. And then cooling. This we are all facing heating issues in our laptops and mobile phones. Consider thousands of laptops are in the same place. How much heat it will generate? So that we have to cool it down. So that is also a very big challenge actually. Now another one main problem is coming: reliability. How reliable this programming is actually. For example, uh, let's say 100,000 or like 1 lakh processors are there, and all of them are working together. But how will you say that okay everything is working always fine? Not possible. Sometimes it's not easy also to say that. So malfunctioning may happen, and you have to take care. How will you take care of that? That is also another one problem. These are all the challenges behind the parallel computation. Now let's talk about what is really a parallel computation. So I hope you all studied the um, basic computation in your first semester course, and you may seen this diagram. Serial, you heard about it. Serial computation. Serial computation. What will do? Your one problem is there. The instructions will go one by one to the CPU, and the CPU will process, and the output will be given. So the problem is broken into discrete series of instructions, and one by one the process will go. That is the way a serial process will happen. For instance, if I want to add 100 numbers, one number will be added with 2, 2 will be added with 3, 3 will be added with 4. Likewise it will go, and it will be done in CPU in a sequential way. But now, instead of 100 numbers, I'm talking about 1 billion numbers or 100 billion numbers. It's a huge task. If a computer, if you give, it will definitely take some time to do all the, even a small summation problem, I mean, addition problem. So, in this case, how to do? I want to reduce the time. Very simple. What we are going to do? Here, only one CPU in a serial processor, but here we are having 4 CPUs actually. Okay, so now what we can do, for instance, we can split the problem into 4. For example, I'm talking about only 100 number. What I will do, first to 25 number will be added by the CPU. Next to 25 will be added by the CPU. Next to 25 will be added by the CPU. Next will be added by the CPU. Now finally, all these 4 results will be summed up. Done. So your summation is done. If you think very carefully, all these CPUs are simultaneously working, parallelly working. So the time will be reduced by 4 times because I am using 4 CPU. Consider I am using 100 CPU, then the time must be reduced by 100. But there is a challenge here. It will never be 100% efficiency because of some challenges. We will see that later. So you may expect, okay, consider in order to I add 100 numbers in single CPU, consider it is taking 4 seconds time. Here it must be done by 1 seconds actually, 1 second, that's it. But it will not really happen in a real life actually. Okay, so this is the difference between parallel and serial computation. If you have any questions, you can ask now, up to now, because after this we are going to talk about a little bit more. Any
Sir,
queries?
they don't have any questions, sir. You can proceed.
What?
Yeah.
Oh, they don't have any questions.
So they don't have any questions. Yeah.
Okay, fine then. Okay then. So now we are talking about basic terminology of a computer. See, although we are like in aerospace, but when you are entering into parallel computation, you must understand something about computers. Without understanding computers, you cannot do the coding properly for the parallel computation. So it is the basic design how it works actually. So it is a memory where your data is stored, and from there it will fetch it to the computation. Then once more it will be bring it back. This is the basic sequential operation how it done. Now how different architectures are there. One sign is flying. he gave a taxonomy actually. So in 1966, so by using that, we are going to split it into different things. For example, four possible classifications. First thing, single instruction, single data. Single instruction means instruction here is program actually. It can be definitely a program. And data. Data means your input. Okay, so single data, single input. Which means what? Single means doesn't mean that only one number or one line program. No. Same program, but different same data actually. This is your I can say like one kind of taxonomy. Second one is single instruction, multiple data. So program is same, but data is different. This is the one we often use in the CFD, computational fluid dynamics. Then multiple instruction, single data. So different programs, but data is same, and multiple instruction, multiple data. So this kind of MISD and MIMD is often used in the satellite data because satellite data is very huge and they use different instructions to do the process. It's not a single program. For example, the satellite data can be anything. It will give bunch of data depend upon your field. For example, you are talking about metallurgy, you metallurgical data, you have to work on in that one. Likewise, you have to take different programming models. Now, single instruction, single data, it is nothing but your serial system actually. So, SIMD, that is single instruction, that is single program, and multiple data. Multiple data means the data or else the calculations done by the processors will be different, but program is going to be same. For instance, if a program I'm saying c equal to a plus b, the same c equal to a plus b will be used to solve, but data will be different. Data is actually maybe a will be different, b will be different for each and every processor. Now this is parallel computer memory. So this is how the computers are connected actually. So this is a shared memory. This is, you can see many often in your laptop systems as well as any desktops. So all the CPUs share a single memory. So it is very easy to program this shared memory architecture, but there are some limitations because all the CPUs are connected with a single memory. Possibility is that um, accessing other people data by another CPU. It may happen. For example, CPU 1 is writing some data here, and CPU 2 maybe replace that data and write it. So very heavy traffic may also happen in a single memory. So we have to go for distributed memory. Distributed memory, here is one memory, one CPU. But it's not easy actually. First thing, like what I can say, like connecting the CPUs are not easy, and also it is not very efficient because more money also you have to spend memory and CPU together. Rather than that, we are going for a hybrid memory. So here, what we do, consider this is one cluster. I mean, it's a whole cluster. This is one memory with a bunch of CPUs. Then it will be connected with another one. We call this one as a single node. For example, this one as a node actually. So here memory will be there and also some amount of CPU will be there. Maybe 12 nodes, 12 processors will be there, for example, with the memory there. Same thing. So these are all connected with network. I mean, network cables will be connecting these nodes actually. So this is our hybrid memory. This is the hybrid memory method often used in many large and fastest computers in the world actually. So because it is very efficient when comparing with the other two. Then other than this, some parallel programming models are there. So if you see very carefully here, I talked about memory architecture, how the memory must be. Here I talked about how the program and data must be. But next one is programming models. Different models are possible. First thing is shared memory. We've seen that what is that actually. Then threads. You can see that in your laptops. You will say, okay, it can do multi-thread. For example, two threads, four threads possible. Which means what? A single processor. I can say like a single. let's say a single processor, the single processor will be having two threads. I mean, this single processor will act as a two processor. Then message passing is next method, like in between processors. For example, this CPU will communicate with this CPU. How? That is by message passing interface. Data parallel is, as I said, it will be used for the big data where we are in aerospace. We don't use that much in CFD especially. And then hybrid model, as you see. So these are all like are different methods, but keep in mind there is no best model here. Every model have their own advantages as well as own disadvantages. Depend upon your application, you have to select. Now threads. You can see this kind of threads in your laptop itself actually. For example, this is a program you are running, and this program will be split into different parts. For example, subroutine one is, this part is called by thread one. For example, in your CPU, four threads are there, for instance, four threads. So you can say like second call will be taken by T2, second thread, and remaining thing will be done by T3 and T4. Likewise. So with respect to time, this threads will process in a different way. For example, uh, POSIX threads and OpenMP are examples for the thread models. Often people use OpenMP in the field of CFD. Okay, by the way, one thing is like all these threads are connected with the memory of the processor actually. Okay, it does not have a separate memory for these threads. All these threads will be connected with the global memory of the processor. Then message passing models. This is like different processors will communicate with them through message, like you are sending some message. Okay, somebody will send some message, and for that reply somebody will send the reply. But here the difference is, in your case, like humans are thinking, but the machine have to decide what to send and what I have to send. So that is your message passing model. So this is very often used in our CFD codes. That is MPI. We call it as, in short, we call it as message passing interface. So message passing interface is called MPI. So this was like started from 1980s, and we gave 1992 a name. This is a standard name actually, MPI 1, MPI 2, and MPI 3. So depend upon the model, some modifications can be done in the programs, but still MPI is the core in the parallel computation. So now how MPA works? Let's say MPA is the default parallel computing method in any industry, in research or in any kind of places. People use MPA actually. So okay then. So let's say this is a array of calculation you have to do. Now this task 1 is nothing but your processor 1. This is processor 2. This is processor n. So this array will be split into pieces. As I said, for example, consider I am doing this up to 75. So what I will do, 51 to 75 will be done by this one. For example, 1 comma 25. First to 25 calculations will be done by first processor. 26 to 50 will be done by second processor. 51 to 75 will be done by third processor. Likewise, how many processor you want, you can make. So a single array calculation will be done by different processors. So this is the way how it works. Now this is hybrid model as we seen. So here we are going to mix the hybrid, like MPI we will mix with OpenMP. So here threads will be running. Likewise, it is a hybrid model, we call it as. So in general, okay, if you have any questions, you can ask now. Then because I am going to move into parallelization of a CFD solver, how it works.
Sir, there are two questions that I got from the audience, from the
Okay.
student. So first question, they're a little bit confused like about single CPU and multiple CPU regarding the performance difference. Like suppose they want to ask like if they're using single CPU, the work suppose some particular task is there and they're working on single CPU and we have a multiple CPU. Whether they're performing the same and what how the performance gonna affect on that. That is the first question they have.
Okay. That I okay. Let's
Yes, sir.
say,
So I think.
uh, yeah, this is your second question. The same thing or different?
So second is that they asked that how to find the number of threads available in the particular memory
Okay.
and how we can increase it.
Okay. I will answer the first one. The second question first. See, number of threads are depend upon your manufacturer. For example, if you are going for any processor, they will say that okay, four threads are there, or else, for instance, they will say okay, this processor have 12 cores, which means 12 processors, and dual threads, which means each processor have two threads. So totally you will be end up with 40 threads actually. Okay, it is purely coming from processor. You cannot increase or decrease later actually. So once you are buying the processor itself, you have to select. Okay. Now, serial and parallel, how it works. Okay, for example, if I'm adding 100 numbers here. So in a serial way, how it will do 1 plus 2. Then it will add the third number. I mean, this is the way how it go. Then it will go add the fourth number one by one. 1, 2, 3, 4. Likewise. Consider this 100 is done here. How it will do? 1 to 25 will be added here. 26 to 50 will be added here. 51 to 75 will be added here. And 76 to 100 will be added here. If you calculate the time, this time consider takes, let's say, 4 seconds. For instance, I'm giving, in order to add 100 numbers, a single CPU takes 4 seconds. Now, if you think very carefully, now their job is reduced 1 by 4th, right? So automatically the time also must be reduced 1 by 4 because all these processes will run simultaneously. For example, first seconds itself, all of them will start actually. So once the calculations finish, how much time it will take? Only 1 seconds, 1 second, 1 second, 1 second. So if you think in 1 seconds, all the calculations are done. Okay. This is the one you want to hear or anything more?
Yes, sir. As per the students, it is clear. They got
Okay.
it.
Okay.
Thank you, sir.
Okay then. So this is basic parallel computation, and I'm going a little faster because I cannot cover many things in a shorter time. So now let's talk about, this is a computer actually, how it works and how parallelization works. Everything is seen, but how we are going to use this in CFD, that we have to see. You all know, those who already know computational fluid dynamics, that is CFD, you generate some mesh in the beginning, that is grid generation. Now the question is, you are having how many number of cells? For example, you may have only 10,000 cells. That is okay. 10,000 cells you are run in a single processor, it is okay. Your laptop will handle. For example, I'm talking about 15 crore cells, or yeah, let's say 10 crore cells. 10 crore cells your laptop cannot handle until unless it is a very special laptop. So now what we have to do actually, I cannot run in a single processor. I want to split the case into different processors. For example, this one model I'm talking about is a lake actually. This lake is very big, and we want to see how the we really interested in studying the um, mixing of some unnecessary components. For example, some people are what I can say, like adding some um, poisonous or toxic liquids here. How that liquid will diffuse in this lake, that I want to study. For example, here some toxic liquids are added, and how much time it will take to reach that here. or else even it is reaching, how much it is diluted, how much effective it is. Those kind of things I want to study. For instance, I'm saying. So what to do? I want to do the meshing. Meshing means splitting that domain into small pieces. That we are doing here. So now the number of cells is approximately, let's say, 10 crore. So in a single processor, we cannot run that. So we want to split that into, we have to run it into parallel processor, which means what? We are going to, as I said earlier, we are going to split into different, for example, 1 to 25, one processor, 26 to 51, same thing. But here, number is increased, number is 10 crore. So if I want to do that, I will run with 1000 processor. Then what will happen? Approximately 10 crore divided by 1000. So each processor will have some amount of cells. Okay, that is called your, that splitting of domain is called your domain decomposition. Now what we are doing, we have to generate the connectivity actually. So in between the processors, how they are connected, that we have to generate. Then we will solve parallelly the solver. Then in order to see the results, we will do the merging of subdomains. I will show you why I am doing that. Okay. So now, as I said earlier, domain decomposition is the first step actually. So now the question is, I can split into different pieces, right? For example, I can say, okay, only these two cells are processed by some processor. This processor is different. Likewise, I can do any random calculations or random distribution. But there is a problem. If you are doing a random distribution, what will happen actually? The communication time, as I said earlier here, connectivity we are generating. The reason is the processors have to communicate among themselves to get some data actually in the calculation of flux in the computational fluid dynamics. Then in order to calculate the flux, for example, this red color cell is actually, these colors are meaning the processors actually. Okay, for example, this green color cell is for example, I'm saying processor number 2. So this green color is solved by processor number 2, this green color is solved by processor number 2. But if you think very carefully, they are not very close, right? Which means it need a communication protocol. It is very heavy and hard to make. So what to do then? We have to split them in a wise way, such a way that the number of processor communication must be less. So we are splitting them in this way. It is random cutting, and here it is distribution of what I can say, like elements in a certain area, so that I can reduce the communication actually. So this is the best way to do and the domain decomposition. Now we did the domain decomposition. Now what we have to do, how to do it? I mean, domain decomposition you can manually do or anything else. We use Mattis. Mattis is a open source software, so it will give the domain decomposition, and connectivity you have to generate actually. So connectivity is little difficult to do, and complex algorithm is required. But if you really want to do, you can do it. It's not, I cannot say not possible. It is easy. So this is the some results after domain decomposition, how it will be. For example, this is a multi-element aerofoil with a different processor. This is belongs to processor number 1, 2, 3, 4, 5, 6, 7 processors shown here actually. So, oh sorry, 8. Here it is 8. Wait. So totally 8 processors. So if you think very carefully, the processor number 1 will solve only this much area. That's it. Processor number 3 will solve only this much area. That's it. Processor number 8 will solve only this much area. That's it. No other places it will solve. So you have to give that much grid file to that processor. So that is the work of a parallel programming engineer. Now, how a general CFD solver works. For example, this is a way how a CFD solver, we start and read the grid file, whatever you are generating, and then time step calculations, then flux calculation. Here itself, we will do the processor communication and boundary implementation together. Now calculate the, I mean, RHS. That is nothing but you are solving the PDE, actually partial differential equation, and then post processing. This is a time loop. So this is the general way how it works. So what I can say, like this is processor number one, processor number two. As you see here, X is different, X1, but here it is X2, Xn, which means some data is different. That data need to be given separately. Then your processor communication types. How the processor communication? As I said earlier, uh, you see here this area. If you see very in a zoom way, it will be like this. For example, this is one cell, and this is another cell. This is cell center and this is cell center. Now these two cells have to communicate to calculate the data here in this interface. I mean, flux calculation have to be done, which means two data is required. One is left side and another one is right side. If you see very carefully here, this cell having one processor belongs and another side is belongs to another processor. Now these two processors have to communicate. Communicate means what? It will send the data of this cell to here, and also it will ask the data for this cell. That's it, nothing else. So what data it will be transferring? It will transfer pressure, temperature, density, and velocity components. That's it. Okay, so this data will be exchanged in between these cells. But how will you do exchange? That is coming under your communication. Okay, we call that exchange called as communication, processor communication. So now it is like point to point communication, which means what? One processor, for example, here, this processor will communicate with only this processor. That is one point. Or else another one is this point P1 will communicate with Pn. That's it. Or else the P1 will communicate with P2. That's it. So this is a single point communication. Okay, that is your point to point communication. Now Now, another one thing is collective communication. Collective communication is the one, like, for instance, single processor. The processor number one is deciding, okay, I have to send information to all the processors. Okay, so it is a serial kind of communication. It will give same data to both guys, actually. That is a collective communication. Collective communication is broadcast. For example, you are listening FM radio broadcast, actually, right? So there is no specific data given to you. It is a common data. For example, news, even you will hear the news and your neighbor will hear the news. Even 10 kilometers away from your house, somebody else is listening the same channel, he will listen the same. That is called broadcasting. There is nothing different. Same data is transferred to everybody. That is broadcast. Then comes to scatter. Scatter is, consider this is processor number one. This processor is sending specific data to other processors. For example, okay, this processor number is 2. It will send some data. Processor number 3, it is different data. Likewise, if it is sending, that is your scatter. Now gather. Gather means from all the other processor, something will be collected. That data will be different, that doesn't matter, but collected by a single processor. For example, processor 1 will collect all the data from the other processors, actually. That is your gather. Then reduction. Reduction is an important function. That is, it will do some arithmetic operations. For example, multiplication or addition, those kind of things it will do. So that we will, all the processors will send some number, but end of the day, a single number will come out of it. Actually, that is your reduction. These are all the collective operations. So this is the way how the processor communication. This is types. Now, as I explained earlier, this is the way how it will do. For example, this is cell number J, this is cell number I. The data have to be given from J to I as well as I to J. That both side is important so that it can do the calculations. So here, like point to point communication is often used in our CFD solver, and also we use broadcasting it sometimes. For example, input data I have to give, I will give to everybody in a single shot. So it's like broadcasting. And Here, blocking and non-blocking communication. It is one communication method actually. Blocking means it's like what I can say. Um, Consider a newspaper person is coming to your house. There are two ways he can do. He can wait till you are reading the newspaper, then he will leave. That is one method. That is blocking communication. Until you read that message, that processor will not do any other process. It will wait for you reading it. Okay, that is blocking communication. Another one is non-blocking, like how your newspaper seller doing now. He just throw the newspaper to your compound, or he will keep it in a box wherever it is belongs to you, which means he don't care whether you are reading it or not. It is not his problem. That is the non-blocking communication method, which means in this case every processor will give the data to another processor, but it will not care about whether the data is sent or whether the data is copied. No, it doesn't care. Okay, that is your non-blocking, but it is very dangerous because it is a important data while calculation. If the data is not properly sent, it is a problem. So what we do, we use non-blocking, and wait time will be given. And actually this non-blocking is given to avoid the waiting time. For example, as I said, like blocking, until the next processor read, this processor is blocked, it cannot do anything. So waiting time will be increased and deadlock will happen. What is deadlock? Consider this processor is sent it something, and it is waiting to get the response from W1. But same time, consider this processor also sent something here, and it is also waiting some response from here. What does it happen then? Both of them cannot give the response because it is waiting for his result. I mean, this processor is waiting for this result, which means deadlock situation. It is very hard to manage. Okay. Now this is blocking and non-blocking. How it happens actually. So now this is the merging. I told you this is the next process, merging of subdomain. Why should I merge? As I said earlier, for example, this is calculated by processor number 1, this is by processor number 2, this may be by processor number 3, and this is by processor number 4. So you will definitely see a cut section here. I mean, because this is the cut in between the processors. So this one we have to avoid, which means what we have to do? We have to do some interpolation. That interpolation is nothing but your merging actually. Okay, so that's why your merging is required. So you can see in the 2D simulation over a cylinder, this is the scenario, and this is the sphere actually. So before merging, you can see it is like some unbiased interpolations have happened. Now here it is good. Now end of the day, like we did the parallel, but we want to see how much performance it is doing. For example, as I said, like I'm adding processor doesn't mean that my performance will be equal. No, it is not possible. Okay, so we have to see some relative performance metrics actually. So first thing is speed up. Speed up is time taken by a single processor divided by time taken by the p number of processors. For example, one processor, it is taking, let's say, as we see, 4 seconds time. Okay, and time taken by the p number of processors, it is taking 1. This is the way we will calculate the. So here the speed up is 4. So see here the linear is here. Linear will be number of processor increase, the speed up will, relative speed up will increase. For example, 30, 30, 40, 40. But in a real time, it will never happen actually. As you see, some of the results which is shown are my published results. You can see here, it always go in a different way. It definitely not go in a um, like very ideal way. Okay, so efficiency also same. Efficiency is very good, gradually drops actually. So efficiency also the same, it will definitely drops. So why it is happening actually? So this is because of parallel overhead. Okay, so that we are going to see what is parallel overhead and how it is happening. Okay, so there are two sources can be reason behind this. Okay, one is like what I can say, like interprocessor interactions. For example, as I said here, this side processor will communicate with this processor. Like definitely the communication will take some time, right? Although you are saying okay only milliseconds, but milliseconds is also sometimes important. The communication will take some time. Then idling. Idling means some processor will not run. For example, 10 processors you are running. One of the processor finished its task earlier, which means it will be waiting for another processor actually. As you all know, in a teamwork, the 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 low speed guy, I mean those who is running the slowest way, slow running guy will decide the fast of the team. Same thing here also. For example, 10 processor, one processor is finishing the task later, then all the 9 processors have to wait, which means idling time. It is not doing anything, just there. That is idling time will reduce the computation, I mean increase the computation overhead. Then excess computation actually. So this is one problem is like you have a very good algorithm in a what I can say, like in a um, serial program, but same algorithm cannot be made for the parallel algorithm. Then definitely it will reduce the computation cost. That is also a issue. Now the question is how the communication ratio must be. So can I have a fast communication? I mean, often I have to communicate, or I will do only computation. It is depends actually. First, what is granularity? Granularity is nothing but the ratio of what computation and communication. So how much computation you are doing in between every communication, that is your granularity. So fine grain granularity, which means what? The communication is much higher actually, almost equal to computation. Then coarse grain, which means what? The communication is very less, computation is more. Now, which one is best? Here also, it purely depend upon which application it is. For example, this fine grain is often used in operating systems actually. This is the scenario. We need communication very often, but in case of computational fluid dynamics, I may prefer coarse grain because I don't want communication, because communication will reduce the, I mean sorry, increase the computation time. So I want to reduce it. So communication I will reduce. So there is no best or worst, it depends upon the application. Now, still challenges. For example, subdomain generation matrix efficient algorithm is required. It is not easy actually. The what I can say, the algorithm development for the uh, connectivity is not easy. Then computational cost actually. Computation cost is also there because to run the matrix you need to put some computation. Then communication process, there are some issues like deadlocks, data loss, and efficiency are there actually. That we have to counter. Above this, we studied about CPU. I mean, your CPU in your computer. But nowadays, people are using GPU. Actually, GPU means graphic power unit, processing unit. So this GPU is done by CUDA or OpenCL models. This is like in your laptops also, at least 500 to 600 cores will be there. But the cores are not that much strong, but a lot of cores actually. So they can split the problem into many small problems and they can solve. That is the advantage of GPU. So I'm not going much deep into GPU because it is not necessary for this talk. However, if you are interested, you go through GPU also. So I'm closing my talk here. Yeah, thank you. If you have any questions, you can ask.
Thank you, sir. So there is one question. So
Yes.
question lies like that. I think you've explained about merging of subdomain. So the
Yes.
question lies like, if we have not a very good high performance laptop or computer, if we divide the components into fragment, can
Uh-huh.
we able to like analyze those
Oh, no,
things?
no, no, not possible. The reason is, yeah, I understand you are having very small computer, so you cannot do together totally, right? So you want to do like this part separately one time, then you will add it here. Likewise, you are asking, right?
Yes, sir. That's what he's
Yes.
asking. Yeah.
Okay, not possible. The reason is you see the algorithm here. This is a general algorithm for a CFD solver for Navier-Stokes equation actually. Okay, so if you see with respect to time, it is running actually. Okay, with respect to time, that loop is running. So every time step you need the neighbor data. Understand? You need the neighbor data, which means if you are running in that way, you are running this one. How you will get the, for example, here one cell is there, it need a neighbor data. There is nothing without that you cannot run the solver actually. So definitely it cannot run. Okay, got it.
Yes, sir. Sir, just give me 2 minutes. Let me ask from the audience if they have any other
Yes,
question.
yeah, sure.
Sir, there is one more question. In the
Yes.
same margin of subdomain, how
Mhm.
do we feed the boundary condition for those particular object?
Okay, I mentioned that, I think, one second. Okay, see here. So the boundary condition implementation and the processor communication will be happening at the same time. So consider this is my boundary in a real time. Uh, this is a wall boundary. Then you will feed some data to run this code as a wall boundary. Same thing I will do, but the data I will take from the nearest processor through communication. That's it. That is the only way we will do. Is it clear?
Yes, sir. So one more question came up. Sir, is there any maximum limit of having machine, the number of machine? Like as you mentioned, 10,000 or something as for a very low performance laptop or desktop.
No, no,
So
no.
at what is the
No, we cannot
limit for
say in
it?
that way. I just gave an example as 10,000. Don't take those numbers as a real number. It depends upon your RAM capability and also your processor capability. Okay. For example, in order to generate that mesh, let's say 10 crore or 12 crore mesh, you need at least 128 GB of RAM actually. Without 128 GB RAM, I doubt it. You can make that much mesh. Okay, one thing, and processing that also, if you are having only one processor but 128 GB of RAM, no problem. It will take at least 1 hour to give one iteration. Consider not 1 hour, maybe at least 30 minutes. I'm talking about at least 30 minutes. That is my understanding at least. So 30 minutes for one iteration. Likewise, you have to run, let's say, 20,000 iteration. How many days it will take? That is the issue. Okay, so the number of cells, everything is depend upon your problem and also depend upon your computational capability, but it
Okay,
is
so
always better to
sir,
maintain
related to
some.
that, sir,
Yes.
sir. Sir, related to that, there is one more question came up regarding machine. That regarding research purpose, do you advise automatic machine that happens in ANSYS and all? So, do you suggest that? Because in automatic machine of that particular component, we don't have a hold on it. But if we want to do it manually, we can hold on it on the number of machine. So, what do you suggest regarding the
Okay.
masters?
for the
Okay,
master student. Yeah.
okay. Here also there is no thumb rule on it actually. What I can say, like automatic mesh, you can do. For example, your problem is very simple. Can you see this problem is very simple problem? It is a sphere, and it is a very simple problem. So automatic mesh will do a better job here, no problem. But for example, you are doing some complicated airplane geometry with the wing, fuselage, everything together. It is a complicated. Then automatic may not help you because, for example, the wing junction, I have to increase the number of cells, or like in the leading edge of the wing, I have to increase the number of cells. Likewise, you understand? So it depends upon the application. But for simple geometry, automation, automate now the algorithms are very good and it can do the job. But only when you are going for some complex geometry and you really require a very good quality mesh, then you definitely have to go for manual way. Yes.
I think, sir, you have answered all the doubts of a student.
Okay.
I think we don't have any other doubt. Thank you so much, sir, for
Okay.
giving a wonderful insight about this high performance computation. Because when I had word with you, even I was not clear what sir is going to deliver today and in the aerospace. But you have clearly given wonderful insight, especially for merging of different domains of or any particular job. And thank you, sir, for your time and accepting our invitation, sir. Thank you
Okay.
once again on behalf of GN University Aerospace Department.
Yeah. Thank you. Yeah. Okay. Bye bye.
Thank you, sir. Have a nice day.
Yeah. You too. Have a nice day. Bye bye.